Hello, STEM Nation. Jeff here, and welcome to episode number 81 of STEM on Fire, where we interview practicing professionals in the area of science, technology, engineering, and math to help guide students that are interested in STEM careers. If you like what you hear, please share it with a friend. Now let's get fired up today with our guest, Alison, and I hope our chat will help ignite your passion towards a STEM career. Alison is a serious mechanical engineer, earning a PhD in mechanical engineering with a focus on sports biomechanics from UC Davis, and is a biomechanics researcher at Nike. Welcome to the show, Alison. Fill in any gaps and share a bit of your personal life.
Hi, thanks so much for having me on the show. I am thrilled to be able to talk to you and your audience about how fun it can be to be a biomechanical engineer. I think you hit the highlights of my credentials, but I think the flip side to that is I've always been passionate and interested in sports, and that passion was ignited when I was very young doing gymnastics, and it's been amazing to combine that passion with a STEM field to be able to think about how people move in a really systematic mechanical way and help create products that change their performance.
All right, thanks for that, Alison, and let's get right in here. So you do have a PhD in mechanical engineering, so you are a serious mechanical engineer, and you're a biomechanics researcher. Could you explain to STEM Nation what that really means?
Absolutely. So in mechanical engineering, you're thinking about how things move. Your first thing that might have come to mind is how an engine in a car works or the aerodynamics of an airplane. But if you really think back to your first basic mechanics class, your first basic physics class, one of the classic examples that comes up is how a pendulum swings. Now, if you take that pendulum and insert a person, that's kind of like a person swinging on an uneven bar. And if you kind of just keep building up those examples, you can think about in mechanical engineering or in physics, you're thinking about how to take the system of things that move and write equations that describe it. And you can apply that to people. And that's, in fact, what I do as a biomechanical engineer.
Thanks for that, Alison. And I got a question of why you went for mechanical engineering with the focus on biomechanics versus going for biomedical engineering with a mechanics focus.
Well, the nice part about any sort of interdisciplinary field is that there's a lot of ways to get from here to there. And I think you outlined two really great ways I could have gotten to where I was. And then there's also a field of kinesiology or human movement science, which I could have done to really end up in a similar place. The reason that I took a mechanical engineering approach is that, first, I like things that I can see. With biomedical engineering, often you're thinking about things on a tissue level instead of a whole person level. And, you can start by thinking about all of these small things and adding them up to try and figure out how the whole person moves. But that involves looking through a lot of microscopes, which I learned very quickly that I was not into. But from a mechanical engineering perspective, you start from the big and you work your way to the small. And the cool part is that we meet each other in the middle, and that we do have to learn a lot from each other's approach in order to get a really clear picture of how your whole body is moving, and then how all of these little pieces add up to that movement.
Yeah, so that's interesting, Alison. I think that's important for STEM Nation to know, if you're looking at biomedical engineering or mechanical engineering kind of with a biomechanics focus, kind of going, small to big or big to small, what are some opportunities out there, Alison, if you're going the mechanical route with biomechanics, maybe outside of the biomechanics research you're doing currently, what are some other opportunities available?
Yeah, the future is bright for biomechanical engineers. I think there's never been a better time to be in the field because at a most basic level, you're thinking about how people move and how people interact with their environments. Directions that you can take that are there's opportunities in consulting fields. Injury biomechanics is really important. If someone were in an accident, understanding how and why they were hurt is really valuable for preventing that type of injury in the future. There's also opportunities to work in the tech space. Apple, Google, Fitbit, they're really interested in how you're moving, why you're moving in those ways to be able to produce products that you interact with. In the sporting good industry, which is where I sit, it's imperative to understand how an athlete moves and what an athlete needs in order to create products that fulfill their needs. So there's a lot of different avenues that just this underlying understanding of how and why people move the way that they do can really be a benefit.
All right, Alison. And I was looking at your LinkedIn profile, and you do have a PhD, and it looks like you actually went on to teach for a little bit. Is that the reason you went on for your PhD, because you thought you're going to be in academia? And I guess the real question is, how important is that PhD in what you're doing today?
Yeah, that's a great question. So you hit the nail on the head. Maybe I'll tell you, if I could start a little bit farther back. So I grew up doing gymnastics, and my coach actually had a PhD in physics. And I didn't realize at the time how unique that was. And it allowed him to talk to us in a really different way than I think other coaches would have talked to me. He talked to me about how if I increased my velocity, we could, by a certain percent, you could increase airtime during your vault. And as a 9 or 10-year-old, I didn't really understand what he was saying, but I knew I wanted to do my best. And so I, enthusiastically nod and say, yes, this is what I'll do. And then when I finally got to high school physics class, it started making sense why he was talking in those ways to us, what he meant. And it really helped me understand that you can apply physics to anything. And I thought it was awfully fun to apply physics to thinking about people and sports. So I wanted to be able to pursue a career doing that. When I went to undergrad, there wasn't really that many opportunities to do that yet. You do need to, many curriculums are set up such that you have to develop a core competency or a way at which a core set of skills that then in graduate work you can apply to 100 different types of problems that may be of interest to you. So as we talked about, I took the mechanical engineering route because I was really interested in the gross movements of a big system or of systems. And then in graduate school, I was able to take that knowledge and really apply it to gymnastics, which was really exciting to be able to bring those things together. And why I pursued a PhD at that time was I really was interested in heading into academia for two reasons. I was excited about teaching, and I was also really excited about having a lab that was dedicated to doing sports research. So I had the opportunity to teach at Ohio State for 2 years, and it was an amazing experience, and was in the process of getting that research program off the ground when an opportunity opened up at Nike to step into already an existing world-class sports research facility with access to some of the best athletes in the world. And it seemed like just a really good match for my research interests at the time.
Yeah, so you're able to pivot. You weren't quite able to do what you wanted to do in academia, and you're able to pursue that at a company, a very large company that had something already in place. So that's really great.
Yeah, and I'd say I got to do a lot of what I like to do at Ohio State. It just was challenging to put together an entirely sports science research portfolio.
Let's transition here a little bit into something that really has you fired up today in the area of biomechanics, engineering, or anything in general.
I'm just so excited about the plethora of tools that are becoming available to just measure and understand how people move and some of the world around us. I can give a couple examples. When I first started in the field of biomechanics, if we wanted to know how an individual was moving or trying to understand how the bones were moving under the skin, we would put markers all over the outside of outside of your body. And we'd say, oh, we know that the skin moves around a little bit, but, this is the best we can do. So this is a pretty good estimate for how your skeleton's moving. Now we still do that. But there are also these tools available, like these X-ray machines that run at take hundreds of pictures per second. So you can have somebody, do a cut in an X-ray machine or do a jump in an X-ray machine and actually see what's happening inside the body. So I think breakthroughs like that in how to measure previously, things that we were unable to see is really exciting. I think another thing that's been really exciting is just the interdisciplinary nature of the field has become more and more welcoming of other people with other skills. So bringing in data scientists and people with machine learning experience to kind of look at the data sets we're able to generate has led to some really insightful observations and new questions for the biomechanics field to chase.
Yeah, I'd like to dig in a little bit, Alison, into that. The big data, the artificial intelligence as it's being applied to biomechanics. Could you go into a little more in depth on that?
Yeah, you see it in a lot of different ways. So some of the more exciting work that I've seen recently is there's researchers that create these really complicated simulations of how your body moves. And they start at, by building each individual muscle and, connect them to skeletons, and then ask questions like, if we activate your muscles in this pattern, how would the skeleton move? And you can use those types of models to answer questions that you could never answer by asking someone to move in front of you. Like you could say, what would happen if this athlete or this individual was twice as strong? Like what type of movements would they be capable of doing? Or for an individual with some sort of neuromuscular or musculoskeletal disorder, you could say, all right, well, how do they have to compensate if they can't activate this muscle in the same way as someone without this disorder? And you can play with these types of questions on these really big models. But previously, it's been pretty challenging because, you kind of put in test the solution or test the question you're trying to answer, and then you come back 3 days later when the model's finally finished running and get some sort of an answer. And I think with some of these big data or just better data analytics processes, able to make the models run faster, learn how each of these individual changes are coupled, and instead of having to run simulations like one at a time and see what happens, you can run many at a time to see what happens. In imaging, like if you go to the doctor and have an MRI taken, doctors have to go through, slice by slice of those MRIs to see whatever structure they're interested in looking at, or pick out maybe a tiny defect that they're looking for. And there's a lot of machine learning and artificial intelligence or even computer vision algorithms that help identify those defects for the doctors so they don't have to go through step by step.
So STEM Nation, listen to what Alison is talking about, right? So it's mechanical engineering, but also there's the big data, the data analytics, how to process large data sets. And a lot of that is all math related. So if you're going off to college and there's an artificial intelligence or a big data type of class, you may want to look at taking something like that maybe as an elective, because that seems to be where the future is headed. Absolutely.
In most machine learning classes, and the best part is you'll recognize most of the math from a linear algebra class that you took. It's the same math, it's just applied to much bigger data sets.
Yeah, linear algebra is the basis for a lot of the AI work. So when you're in that linear algebra class in college and you're like, when would I ever use this? It would be used all the time. So, speaking of college, Alison, getting through college, you went all the way through to your PhD and you actually did some teaching at Ohio State. We're looking for some guidance, back when you were 18 heading off into college, and also some insights that you may have as a professor. What kind of attributes you see in successful students?
Things I needed to learn when I went to college were I quickly realized I had never really been academically challenged in that way, but until I got to college. And then suddenly classes were very hard, and you were taking a lot of very hard classes at the same time. And so I would say my first piece of advice is be patient with yourself and just keep trying, because you'll eventually learn how you learn. And if somehow you learned that before you went to college, that's really great. Go send your high school teachers a thank you note. I think just that measure of perseverance and trying to learn the material so that you understand it rather than trying to learn the material so that you pass a test is just a step along your academic career. And the sooner you make that, the more you'll get out of your classes.
Yeah, and that's interesting. That's come up time and time again, Alison, on the podcast from folks that went through is, learn the material. Don't be studying it just to get the A. Actually learn the material. You'll be better off in the end doing that. And I've said this before on the podcast is I was one of those that I would study to get the A. And I look back and it's like, gosh, I wish there's classes where I'd actually would have tried to learn the material and not try to get the A. I would have been better off for that.
Yeah. And sometimes not getting the A is also a little bit freeing. I definitely saw students who had, impeccable, amazing high school and undergraduate careers. And then where they really met their first challenge was in grad school, where maybe they weren't going to get an A or it took longer to learn something than they expected it would take. And just know that everybody hits that point at some point. And it's nice to get over that hurdle a little bit earlier in your career, because then you develop this sense that you'll be able to do it.
All right, Alison, and we're going to head over to the lightning round. Are you ready?
Yes.
What is the best piece of advice you've ever received?
Don't be afraid. A bias towards action, even if it's the wrong action, will end up working out better for you in the long run than sitting there and trying to overthink the problem.
Yep, and if I were to paraphrase that, it's just start taking action and correct along the way.
Yep.
And a personal habit that contributes to your success.
I really try hard to prioritize my time. And I'm sure that's not an original answer, but just thinking through, there's 100 things that we could do or should do, but picking a couple that I really want to do well and investing my time into doing that is really fulfilling.
And a favorite internet resource or phone app?
Oh, I look at Twitter way too often.
And if you had to recommend one book, what would that be?
My style of books varies widely, but recently I enjoyed 5 Days at Memorial. It was kind of the story of what happened in the aftermath of Hurricane Katrina. And I didn't enjoy it because it was a uplifting story, but it was a really insightful look at how people respond to emergencies.
All right, Alison. And with that, we're going to say goodbye, but we're going to ask you for a piece of parting guidance for STEM Nation, and then we will say goodbye. I
was very lucky because I kind of had a sense of what I hoped to do. And then somehow by all the stars aligning, good luck and good preparation, I ended up doing it. But know that I'm the exception rather than the rule. And you don't need to know what you want to do, with your career, with your life, but don't be afraid to try something. And if it doesn't work, don't be afraid to try something else. All right, Alison. And with that, we will say goodbye. It was great talking with you. Right. Thanks for the opportunity. Yep. Thanks, Alison. I hope you enjoyed that chat today with Alison. You can head over to STEMonfire.com, subscribe to the email list to keep up with the latest happenings, and be sure to subscribe to the podcast on your favorite podcast player. And tune in next week, we talk with Mel, who is a consulting engineer. Until next time, I hope this chat has helped ignite your passion in STEM.